the alternative, which is to make a sparse measurement. And the reason is the one which I explained before. The longer it covers in time, the higher the resolution will be. So here is the flash, and it caught the voltage at this value, or the valve stem at that angle, and the next time it caught it here, and the next time it caught it here, and here, and here, and here. It goes down, and then another one starts, and it goes down. So this is a stroboscopic image, and this table of sparse data has all the data that there is in it, to the extent that we're making enough signal-to-noise ratio on these points. So we maybe have a confusion for a moment that we have the integer wrong in this, but after we look a little bit and try to enhance the resolution, we'll soon become aware which is the right integer number. So what's important from a measurement science point of view is that if you make n measurements of this and you have a certain amount of signal-to-noise ratio, then the more measurements you make with the square root of the n, you get better noise, better signal noise, and with the number of measurements, you get more leverage on fixing what this frequency ratio is. So that gives you an n to the 3/2 power scaling, and there's no other way in physics where you can get data so powerfully. So I'd like to show this then on the more realistic time scale. If we looked at that optical frequency wave edge on the same time scale that we could see these time pulses coming, and these time pulses only last 1/1000th of a second. No, I beg your pardon. They are separated by 1/1000th of a second. They only last 1/100th of a millionth of a second, 10 to the minus 14 seconds, 10 femtoseconds. And when this flash comes, and we look to see how it impacted on this, it practically looks continuous. Here it is on a magnified scale, and we can see one of those optical cycles here. And that more or less lines up with one of these strobe pulses. The laser technology is such that the pulses are around 3 optical cycles wide. And this is fairly realistic representation of what they look like. And then 5 million cycles later, or 500,000 cycles later, depending what the exact parameters are, this happens again. And a little bit of reflection will show you that if the alignment of this strobing and this strobing catch the same kind of wave configuration, that must mean that there is an exact integer relationship between these every time we see it. I don't know what the integer is, but the fact that this lines up exactly proves that it's an integer. So that means each of these strobe pulses would have the same shape, and we're going to need that property, and so that was one of the issues of our design for this. So let me talk about how to design this. Well, what I show you here is a calculated wave, and it's a wave which has this long oscillation period, plus a wave of the same size, which is oscillating twice faster, plus waves 3, 4, and 5, and you see it's starting to get more narrow, and if you add up to the 10th harmonics, you see what's happening is that it gets quite narrow. So we add 10 waves, we have 10 times the power, and we add 10 waves, and we have 10 times the frequency, so we have 1/10 of the time duration. So this gets extremely powerful. And if we thought about the number not being 10, but the real number, which is a few million, you take a little bit of laser power in each one of these modes, you get them all synchronized so that they have their peaks at the same time. This is going to be seriously intense laser power. And oh, did I mention that the time got shorter by 1 million as well? So all of that average energy has got to be emitted in this tiny little burst. It's really strong. So that was the secret, which nobody knew was going to be the secret, of getting this white light, which we're going to need, that's going to be the optical comb. So Mr. Fourier teaches about this kind of stuff. If you have repetitive combs in time, it makes a comb in frequency space. And the longer you run in measuring time, then the more narrow the comb lines are. If you have started with combs in frequency spectrum, like I just showed you, that makes combs in time, and the frequency width that you use controls how short the time pulses are. So it's sort of like undergraduate mathematics, but for some reason, in everybody that I've talked to, the mathematics didn't go that far. It stopped just with one pulse. And we could have had this joy years ago. There's one little thing which I didn't tell you about yet, and that is about how we make these pulses. Here is a picture of a femtosecond laser pulse, and it's getting amplified in this region of the laser. Here's a partial mirror that's going to couple out a tiny little piece of the beam, and however the pulse looked then, that's what you get when it goes out. But as it's inside, you'll see that the shape is changing. And the reason for that is that the shape of this envelope, that's controlled by the speed of the group velocity. Whereas these little waves that are in here are controlled because they have to be standing waves on this whole path. So this is always evolving. When it hits the mirror, it's whatever it is. And one of the pulses comes out, and the pre-central pulse is a little taller. And here the trailing pulse from the central is a little taller. So this effect is upsetting that exact synchronizing business that I was talking about before. It means that there's a little bit of extra phase in this, and we're going to have to cope with that in our thinking. So here's the way that the pulses are coming out. We see them as a few cycles underneath this envelope. Then after a huge long time, we see it as another pulse. And there's just a little tiny drift between the pulse matches. And here's another little tiny drift, twice that much. And so this, I've explained to you, and I hope that you can start to believe that this comb of pulses will get this comb of frequency components. And I've just told you that they might not be synchronized. So if we follow the consequences of that, we follow this spacing down, and it doesn't line up with 0. So we're going to need to know this offset, and we're going to need to know the harmonic number, and after that we know what the optical frequency is. So here's the deal. From microwave frequencies to optical frequencies, and we just have 2 parameters to represent it. So we're really cooking on this track. Oh, I keep forgetting, I have no way at this point to tell you how to make this comb. So this is sort of where we were in 1999. Then I went to a conference. Okay, so let me just do a little advertising. A lot of people ask questions about how this works. So these colleagues of mine, Steve Cundiff and Jun Yi, we've made a paper for the Scientific American. And the subject of this finally boiled down in just one sentence is that the comb is a revolutionary kind of laser light that has properties that make possible more precise atomic clocks and lots of other applications. And I'll tell you, the last one that I tell you about is medicine, and I'm really excited about it. So here's this comb just to remember how that looks like. The place you can find it is April 2008. I am really surprised at this. Let me change lasers here. I always need some. You need more lasers. So, if you want to read the professional level of this discussion, it's in PhysRev Letters, and it was a celebration of our success. Diddams et al. Is a Boulder group. Ranka et al. Is at Lucent, and he's the young man that came up to me 4 or 5 days ago and said I was the one that helped in this project. I'll explain that in a second. Holzwarth et al. Are from the Max Planck in Germany. So more advertising. So now the way that my colleague in Munich used this comb idea says, well, okay, I don't know how to deal with this frequency offset, but I do have apparatus that lets me deal with these frequencies that are pretty large. So he was using atomic clock, a mode-locked laser, and the rep rate was there, and then an optical fiber. And he got a little bit of comb. It was 5% bandwidth or something. And they published their paper in April 12th. It was the first time this coherent method from microwaves to optics had been used. It had 2 huge table worths of stuff because this isn't the whole idea at this point. What's needed is what I learned in a conference in Baltimore late at night, nearly the last paper in this CLEO laser engineering conference. in which a young guy, his postdoc is nearly finishing, and he wants to do something dramatic. So, okay, what can you do? You could use the strongest possible laser that you have, and you could focus it into the smallest possible space that you can have, and something's going to happen. And, okay, that's not very exciting because the light just diverges and it's all done. But suppose that you had something like this. Here is the result of careful cleaning of some glass rod and a bunch of glass tubes, and you stack them all up, and finally it looks a little bit like this, about this size even. And it's got all these 20 or 50 rods and tubes in it. And you take it to the people at Bell Labs that make fibers, and you say, please turn this into a fiber. So in a few days, they give you back 20 kilometers of glass fiber wrapped on a little spindle, which is what you had given them, but slightly different shape, different aspect ratio. So this space now is no longer the size of the 1 millimeter rod that it originally was. This is now 2 micrometers, and 2 micrometers is about the same as the wavelength, within a factor of 2 or something. So if you start squeezing something that is megawatts into few microns, this makes an electric field that's as strong as the electric field that holds atoms together. So you're going to shake the holy heck out of these molecules that are in here. And what happens? Well, red comes in, green is evolved, purple is showing up. Now, I saw that picture, I almost died, because I could see this baby is pulsing every time that pulse comes to it. So here is all these colors that I've been dreaming about, and they're all there, just simple. How beautiful is that? I've got to get some of that fiber. So, I mean, it's a whole new epoch. I can see that. I've got to have it. Okay, so we did the gentlemanly thing, right? We went to the Lucent laboratories, and he was going to be our collaborator. We're going to have a joint project between the National Institute of Standards and Lucent. Well, now the lawyers come into it, and you know how that story is going to come out. We've never used this stuff. We've had this for years. We've never seen anything to do with it. It was just brought back from the storeroom. But you want it. It must be valuable. Consequently, no, thank you. So that was extremely disappointing. That was May, I think this conference was, and we started like 2 days after that. I was then in Germany, and a long-distance phone to Bell. I called up everybody that I knew that was influential. We just couldn't get past the lawyers. However, in September or October or something, I got an envelope. No return address, handwritten label, and it was empty. Not quite empty. Actually, if you looked really hard, there was a piece like this inside. That is so thin, it's as thin as these things that we carry around on us, on this whole diameter, and inside is this microstructure. So this is a tool, and thanks to an unnamed colleague in the Bell Labs, we got 2 feet of this, and that made amazing, amazing properties. So scientists and engineers, you know, we talk about frequency. Okay, you put frequency in the wire, and you get, on the other end, you get frequency out, no problem. Now look at this stuff. You put in 800 nanometers in the red, and what comes out? Green. And you put in a little bit more power, and even more amazing color change come. But again, this is all synchronous. Every one, think of this as those little comb lines. There's zillions and zillions of them. They're very close together. And every one of those is oscillating in the same phase relationship, all timed by the synchronizing that came from this. So this is some kind of a new measuring capability, which is going to really revolutionize the world. So here's, in our lab, what happened. We put in the bandwidth this much, and we got out this much. If you put it on a grating and look at what the spectrum is, you put in red and past the double frequency, you got light out. Or by this time, we had gotten a little bit better technically, and we had an instrument that could stretch the fiber slightly. So we focused down with a microscope lens. It's red going in, you can hardly see it, and it's white coming out. So our idea then was to take this red light and put some of it through a crystal that would be nonlinear, and that would produce all this comb structure, but at a higher frequency. And so we were going to frequency double these and compare them with the blue, sorry, I want to compare the blue end of the main comb with the red end of the doubled comb. Anyway, if you work through the algebra, what happens is you can measure that offset frequency directly. And so it shows up in the spectrum analyzer